Welcome to White Space, what actually exists beyond the edge of everything we can see. Put this on in the background, close your eyes if you want, and let the story carry you. There is a particular kind of silence that comes with looking up, not the absence of sound, but the weight of a question too large to hold. For as long as we have existed, we have looked at the night sky and felt it, that pull towards something we cannot name, something vast and indifferent and beautiful. Every civilization that has ever drawn breath on this planet turned its eyes upward sooner or later. And every one of them asked the same thing: how far does it go? Today we are going to find out, or at least we are going to try. We will leave Earth behind and travel outward past the frozen edges of our own system, past dying stars and starless worlds that drift alone in permanent night. We will cross the gulf between galaxies, look into the throats of black holes, and press up against the very edge of what can be seen, and then we will take one more step beyond it. This is a journey measured not in kilometers, but in comprehension. Let us begin. The first thing to understand about leaving our solar system is just how long it actually takes, even for the fastest things humanity has ever built. Since the middle of the 20th century, we have been throwing metal into the dark. Probes, scouts, messengers, instruments of aluminum and circuitry launched on thin columns of fire, then coaxed into trajectories that would carry them faster and farther than any previous object in human history. Several of them have now traveled so far that the sun itself has shrunk to little more than a bright point among other bright points. Consider what that means. Voyager 1, launched in the autumn of 1977, has been traveling continuously for nearly half a century. It moves at roughly 17 kilometers every second, a speed that would take you from London to New York in under 4 minutes. And yet at that pace, it took decades to exit even the outermost boundary of the sun's direct influence. As of today, Voyager 1 sits approximately 160 astronomical units from the sun. 1 astronomical unit is the distance between the Earth and the Sun, around 150 million kilometers. Multiply that by 160, and you have a number the human brain quietly refuses to process. Voyager 1 is the most distant human-made object ever to exist. It is also, by any reasonable measure, already lost. Its power source is nearly exhausted. Its instruments are switching off one by one. Soon, the last signal will fade, and it will simply continue, a silent artifact tumbling through interstellar space, carrying a golden record with the sounds of a world it will never return to. Before Voyager, there were the Pioneers. Pioneer 10 launched in March of 1972 and made the first direct passage through the asteroid belt, a region once considered potentially impassable. It reached Jupiter in December of 1973 after a journey of more than 600 days. The images it sent back changed our understanding of the largest planet in the solar system, its atmospheric structure, its radiation belts, the behavior of its magnetic field. Most strikingly, measurements confirmed that Jupiter radiates more thermal energy than it receives from the Sun, which pointed toward heat sources deep within the planet's interior, a discovery with implications for how we model gas giants everywhere in the universe. Pioneer 11 followed a different path. Its instruments swept across Saturn and returned some of the first close measurements of that planet's ring system and magnetic environment. Data from the probe allowed scientists to characterize 2 of Saturn's moons, Titan, already suspected of harboring a thick atmosphere, and Mimas, whose surface would later reveal a striking and enormous impact crater. Both Pioneers eventually went silent. Pioneer Wellen in 1995, Pioneer 10 in 2003. They are still out there drifting at roughly 12 kilometers per second, but we will never hear from them again. Then came the Voyagers. Voyager 2 launched on the 20th of August 1977, about 2 weeks before its twin. Its trajectory was more ambitious, designed to exploit a rare planetary alignment that allowed it to visit not just Jupiter and Saturn, but Uranus and Neptune as well. This alignment occurs only once every 175 years or so, and mission planners seized on it. At Jupiter, Voyager 2's cameras captured something remarkable, evidence suggesting that beneath the frozen crust of the moon Europa, and perhaps Ganymede as well, there might be vast liquid water oceans kept warm by tidal heating. This observation, tentative at the time and still unconfirmed by direct contact, has since become one of the most discussed possibilities in the search for life beyond Earth. At Saturn, the probe added new satellites to the catalogue and refined measurements of the ring system structure. At Uranus, it discovered 10 previously unknown moons and confirmed the planet's ring system, which had only been suspected. Neptune proved equally generous 6 new moons, a confirmation of rings, and the detection of a massive storm system in the southern hemisphere. Neptune's gravitational influence bent Voyager 2's path downward out of the plane of the solar system, ensuring it would not approach any other major bodies. But its scientific mission continued measuring the properties of the solar wind as it weakened with distance, probing the heliopause and building a picture of the boundary where our sun's influence ends and interstellar space begins. Voyager 2 is now approximately 130 astronomical units from the Sun and receding at around 15 kilometers per second. In roughly 42,000 years, it will pass within a few light years of a dim red dwarf called Ross 248 in the constellation Andromeda. In 300,000 years, if nothing intercepts it, it may drift past Sirius, the brightest star in our night sky. No one from Earth will ever confirm that passage. The most recent probe to join this exodus is New Horizons, which launched in January 2006. Its primary mission was Pluto, the distant, half-frozen world at the edge of our solar system's known territory. The probe reached Pluto in July of 2015 and returned images that astonished planetary scientists. Pluto's surface was geologically complex, marked by vast nitrogen ice plains, towering mountain ranges of water ice, and what appeared to be a heart-shaped region of extraordinary brightness. Its moon Charon, half the size of Pluto itself, bore features that suggested violent geological history. New Horizons continued past Pluto and into the Kuiper Belt, visiting several smaller objects and expanding our knowledge of the solar system's cold outer rim. By the late 2030s, New Horizons will have traveled 100 astronomical units from the Sun. Its power will be gone by then. It will join the pioneers and voyagers as a kind of permanent dispatch, a message in a bottle thrown into an ocean without shores. These machines are extraordinary. But they are also humbling. At their speeds, reaching even the nearest star would take tens of thousands of years. We are barely at the door. Let us now pass through it, 11 light years from Earth in the direction of the constellation Virgo. There is a star that most people will never see with the naked eye. It is too dim, too quiet, too far. Its name is Ross 128, and by itself it warrants only mild interest. What makes it remarkable is what orbits it. Ross 128b is one of the closest known potentially habitable exoplanets. Its mass is estimated at roughly 1 1/3 times that of Earth. The temperature range on its surface, under reasonable assumptions about its composition and reflectivity, could fall within a span compatible with liquid water, somewhere between about 10 degrees below zero and 20 degrees above. That is cold by most human standards, but not prohibitive for life as we understand it. Ross 128b orbits very close to its star, completing a full circuit in just under 10 Earth days, at a distance about 20 times smaller than the gap between Earth and the Sun. The star itself is cool enough that this close proximity still places the planet within what is called the habitable zone, the orbital range where surface temperatures could permit liquid water. What makes Ross 128 especially interesting as a host star is its temperament. Red dwarfs, the most abundant type of star in the galaxy, are frequently violent. They flare, they spit high-energy radiation that can strip away planetary atmospheres over millions of years. Ross 128 is comparatively well-behaved. Its luminosity is stable. Its flare activity is modest. This gives Ross 128b a better chance of having held onto an atmosphere long enough for something meaningful to happen on its surface. There is one more reason to find this system intriguing. It is moving toward us. In approximately 79,000 years, Ross 128 will become our nearest stellar neighbor, overtaking the Alpha Centauri system. Whatever we might want to do with it someday, we are already drawing closer. Moving on, 12 light-years from Earth, we find Luyten's star, also known by its catalog designation GJ273, where Ross 128 has one confirmed world in a favorable orbit. Luyten's star has a small collection of them. The star is an orange-tinted red dwarf, significantly cooler and dimmer than the Sun. The most intriguing of its confirmed planets is Luyten b, a super-Earth roughly 3 times the mass of our planet, orbiting close enough to its host star that despite the star's faintness, the amount of stellar energy reaching it is not entirely unlike what Earth receives from the Sun. Surface temperatures on Luyten b could potentially fall between about -14 and +19 degrees Celsius. Whether there is an atmosphere thick enough to distribute that warmth and what that atmosphere might consist of remains entirely unknown. A second confirmed planet, Luyten c, sits much closer in. It receives intense radiation and is almost certainly tidally locked, one phase permanently baking in stellar light, the other in permanent darkness. The temperature gradient between those two hemispheres would produce winds of almost unimaginable force. There are also 2 additional candidate objects in the system suspected to be ice giants with orbital periods measured in hundreds of days. They lie well outside the habitable zone, where temperatures would plunge to values hostile to any chemistry we understand as life-supporting. Luyten's star, like many in this neighborhood, is a world builder that makes us wonder. Close enough to study in detail with future instruments, far enough that we can barely guess at what we might find. Continuing outward nearly 17 light-years, we arrive at Altair. And here everything changes. This is not the quiet dimness of a red dwarf Altair blazes. Its luminosity is 11 times that of the Sun. Its mass is nearly twice as great. Its surface burns at temperatures of 7,000 Kelvin near the equator and closer to 8,500 at its poles. That temperature differential between equator and poles points to something extraordinary about Altair. It rotates at an almost violent pace. The star completes a full rotation in less than 9 hours. For comparison, the Sun takes about 25 days. The consequences of this extreme spin are structural. Centrifugal force has flattened Altair into something closer to a disk than a sphere. Its equatorial diameter is roughly 22% larger than the distance between its poles. The stellar matter at the equator moves at approximately 286 kilometers per second. In 2007, Altair became the first star beyond our own Sun to be directly imaged in enough detail to resolve its surface features. This confirmed what theorists had long predicted: an oblate shape with darker, cooler banding near the equator and brighter, hotter polar regions. Surrounding the star is a haze of gas and dust that scatters its light in every direction, producing what amounts to an enormous diffuse ring of dispersed starlight. No planets have been detected within this system, but the observation opens a question. Would they even survive the radiation environment this star produces? 25 light years out, we encounter a different kind of system entirely. Fomalhaut is a name with ancient roots. It appears in the star catalogues of Islamic astronomers and later in European astrological traditions as one of the 4 royal stars of Persia. For a long time, it was understood as a single object. Modern observation has complicated that picture considerably. Fomalhaut is in fact a triple star system. Its 3 components are gravitationally connected, though spread across an enormous volume of space, the outermost members separated by over 3 light years. If you were standing in the night sky of a planet near the system's center and looked toward its farthest companion, that star would appear not as a point but as a faint smudge, surrounded by its own subtle glow. The primary component, the one that has carried the name Fomalhaut since antiquity, is young, blue-white and luminous. Its surface temperature approaches 8500 Kelvin. Its luminosity is 16 times that of the Sun. It is also surrounded by a disk of protoplanetary dust and gas, divided into distinct segments, beginning at a distance of over 100 astronomical units from the star. The inner portions of this disk are actively processing material, collisions between planetesimals releasing fresh clouds of pulverized rock and ice that replenish the disk structure. For years, astronomers believed they had detected a large planet orbiting within this disk. It was given a name, Dagon, and was studied with considerable interest. Later observations, however, suggested that what had been seen was not a coherent planet at all, but a diffuse cloud of debris produced by a collision between 2 large objects in the disk. The planet may never have existed. What appeared to be a world turned out on closer inspection to be a scar. The second member of the Fomalhaut system is an orange dwarf about 70% as massive as the Sun. Recent spectral analysis suggests it may host a planet of its own, a body somewhere between half a Jupiter mass and nearly 2 Jupiter masses with an orbital period of roughly 25 years. But this detection is not yet confirmed, and it remains one of the more intriguing loose ends in nearby stellar astronomy. The third component is a small red dwarf. It takes approximately 20 million years to complete a single orbit of the primary star. In the entire age of the Fomalhaut system, it has circled its larger companion perhaps 20 times. 37 light years from Earth, we reach the last stop in this portion of our journey, Arcturus. It is the brightest star in the northern sky, orange, enormous, visible to the naked eye even from light-polluted cities. But its brilliance is a kind of borrowed time. Arcturus is dying. Its story began much as the Sun's did. A cloud of gas collapsed under gravity, temperature and pressure rose at its center, and thermonuclear fusion ignited. For billions of years, it burned hydrogen steadily, converting fuel into energy and helium in equal measure. But that phase is now largely over. The hydrogen in its core is mostly gone, the star has begun to fuse helium, and as it does so, it is expanding. Its radius is now 25 times that of the Sun. Its luminosity, driven not by intense surface temperature but by sheer surface area, is 170 times greater than the Sun's. Arcturus is the most conspicuous example this close to Earth of what awaits our own star several billion years from now. The same physical process, the same inevitable expansion. Any planets that once existed within the inner regions of the Arcturus system would long since have been consumed by the swelling stellar envelope. What we are watching from a comfortable distance is a preview of an ending. Arcturus is also a notable member of a structure much larger than itself. It is the dominant star in what is called the Arcturus stream, a collection of 53 stars moving together through the galaxy on a similar trajectory. This is not a cluster born from the same cloud of gas. It is the remnant of a dwarf galaxy, consumed by the Milky Way roughly 2 billion years ago. The stars that once belonged to that smaller galaxy now drift through our own, stripped of their original home, their shared motion, the only evidence that they were once part of something else. In a few billion years, Arcturus will shed its outer layers in a slow exhalation of gas and dust. What remains at the center, dense, hot, stripped of fuel, will be a white dwarf the size of Earth, the mass of the Sun fading across timescales longer than the current age of the universe. We have now looked at neighbors. Let us look at something dying on a grander scale. In late 2019, observatories around the world began recording something unexpected from a star in Orion. Betelgeuse, the bright reddish point marking the right shoulder of the hunter, was fading. Within a few months, its luminosity had dropped by more than a third. Social media and science publications alike filled with speculation. Some researchers openly discussed the possibility that the star was on the verge of exploding. It did not explode. By the spring of 2020, Betelgeuse had returned to its normal luminosity. Analysis over the following year pointed toward an explanation. The star had ejected a large mass of superheated gas, which cooled as it traveled outward and condensed into a cloud of dust that temporarily obscured part of the stellar surface. The event, called the surface mass ejection, was unlike anything astronomers had previously recorded from a star of this type. It confirmed that Betelgeuse is in a late and profoundly unstable phase of its life. Betelgeuse is a red supergiant, one of the largest objects that can exist within the constraints of stellar physics. Place it at the center of our solar system, and its surface would engulf everything inward of Mars. Its diameter fluctuates over cycles that are difficult to pin down precisely, but estimates suggest it may be somewhere between 700 and 900 times the diameter of the Sun. Its mass is roughly 17 times that of our star. Its luminosity ranges from 90,000 times that of the Sun at minimum to 150,000 times at peak. These variations arising from the turbulent, pulsating nature of its outer layers. Despite this extraordinary energy output, Betelgeuse burns cool by stellar standards. Its surface temperature sits around 3,500 Kelvin, firmly in the red part of the spectrum, which is why it glows with that distinctive reddish-orange hue visible even to the naked eye. The star formed approximately 8.5 million years ago from a gas cloud that compressed and heated under gravity until thermonuclear fusion began. That beginning initiated what is known as the main sequence, the long, relatively stable phase during which a star burns hydrogen in its core. For a star as massive as Betelgeuse, that phase was rapid by astronomical standards, lasting only a few million years before the hydrogen reserves were depleted. Heavier stars consume their fuel faster, and they pay for their brilliance with shorter lives. When core hydrogen was exhausted, gravitational compression resumed. The core heated further and helium fusion began, producing carbon. The outer layers expanded dramatically, and the main sequence star became a red supergiant. Now the star is working through successive layers of fuel, helium, carbon, oxygen, silicon, producing heavier elements at each stage. This process is building an onion-like interior structure with an iron core forming at the center, surrounded by concentric shells of lighter elements still undergoing fusion. Iron is the endpoint of stellar fusion. Unlike lighter elements, iron does not release energy when fused, it absorbs it. Once an iron core accumulates beyond the critical mass, known as the Chandra's Har limit, the core can no longer support itself against gravitational compression. The collapse that follows happens in less than a second. The core shrinks to an object perhaps 20 kilometers across. The outer layers, falling inward at a fraction of the speed of light, slam into this newly formed core and rebound in a shock wave of almost incomprehensible energy. This is a core collapse supernova. The electromagnetic energy released in that explosion can briefly outshine entire galaxies. The shockwave propagates outward through the stellar envelope, fusing heavy elements, gold, platinum, uranium, that no other process in nature can produce at scale. These elements are scattered into the surrounding interstellar medium, where they will eventually be incorporated into new stars and potentially new planets. What remains at the center depends on how much mass falls back after the explosion. If the remnant core is between roughly 1.5 and 3 times the mass of the Sun, the result is a neutron star, an object so dense that a teaspoon of its material would weigh more than a mountain. If the remnant exceeds that upper limit, gravity wins completely and the collapse continues without limit. A black hole forms when Betelgeuse explodes, and it will, though no one can say whether in 1,000 years or 100,000, the event will be visible in daylight from Earth. It may cast faint shadows at night. It will dominate the sky for weeks, perhaps months. Then it will gradually fade, leaving behind a nebula of expanding gas, and either a neutron star or a black hole at its center. The explosion poses no threat to Earth. Betelgeuse is between 500 and 650 light-years away, far outside the range at which a supernova could damage planetary atmospheres. What reaches us will be light, gamma rays attenuated by distance to insignificance, and in 6 million years a thin, cool whisper of ejecta that will barely interact with the outer solar system. For us, the event will be pure spectacle. Not all worlds exist in the shelter of a star, some travel alone. The idea that planets could exist unbound to any stellar system. Adrift in the open interstellar medium, receiving no light, sustained by nothing but their own residual heat and whatever chemistry their interiors allow, was once a fringe speculation. It is no longer. Observations have confirmed the existence of these objects, though they remain among the most difficult things in the universe to detect, precisely because they emit no visible light worth speaking of. They are called rogue planets, or free-floating planets, or sometimes planemos, a name reflecting the debate about what category they belong to. The term captures a physical fact. These objects have planetary mass, but no host star. They are not stars themselves because they lack the mass required to ignite nuclear fusion. They are something in between, or something outside the categories we built to describe things we understood. The closest confirmed rogue planet to our Sun sits approximately 7.25 light-years away, detected in 2014 by an infrared space telescope. It cannot be observed in visible light. Its surface temperature is estimated between roughly -50 and -13 degrees Celsius, far colder than any known planetary surface receiving stellar radiation. Its mass is thought to fall somewhere between 3 and 10 times that of Jupiter, placing it in the range where interior heat from gravitational compression and radioactive decay could sustain significant internal activity. In 2016, spectroscopic analysis of this object revealed evidence of water in its atmosphere. Not liquid water at the surface. The temperatures there are far too low, but water in the form of ice clouds suspended in an atmospheric layer where conditions produce water vapor that freezes into tiny crystalline particles. The existence of water in this cold, dark, isolated object raised an obvious question. Under the right circumstances, could an environment like this support anything? Modeling suggests that the lower atmosphere of a sufficiently massive free-floating planet could be warmer than the surface indicates. The thick hydrogen envelope acts as insulation, and deeper atmospheric layers may maintain temperatures that are, by some definitions, moderate. Whether anything could make use of those conditions is speculative, but the speculation is not absurd. There is also the question of how rogue planets come to exist at all. One possibility is that they begin as ordinary planets, formed in the protoplanetary disk of a normal stellar system. in the usual way, accreting mass through collisions and gravitational collection of gas and dust. Something then disrupts the system, a close pass by another massive object. A gravitational interaction with a larger planet in the same system that causes the smaller one to be flung outward at escape velocity. A collision between two planetary systems in a dense stellar cluster. Any of these could eject a planet from its orbit entirely, leaving it to continue on a hyperbolic path into interstellar space. The other possibility is simpler and in some ways more unsettling. The object never belonged to a star at all. It formed directly from a collapsing gas cloud, just as a star does, but the cloud was not massive enough to achieve nuclear ignition. Soup-brown dwarfs, some researchers argue, are simply failed stars, objects that tried to be suns and fell short. The distinction matters for what these objects might look like inside and for how common they are. Estimates derived from large-scale gravitational microlensing surveys suggest that the Milky Way may contain tens of billions of free-floating objects with planetary masses. Some surveys have suggested the number could be as high as 100 billion. If true, there may be more rogue planets in our galaxy than there are stars. Most of them we will never see. They drift in the dark, cold, silent, each one a world that no one will ever visit, orbiting nothing, bearing no name. New tools are being developed to find them. Microlensing surveys, which detect these objects by observing how their gravity briefly bends the light of background stars as they pass in front of them, are becoming more sensitive and more systematic. Future space observatories and dedicated ground-based campaigns will almost certainly reveal orders of magnitude more of these objects than we currently know. What we will find when we look more closely is still genuinely unknown. In theory, a rogue planet moving through the galaxy could eventually be captured by a star's gravitational field and drawn into orbit around it. The probability of any given rogue planet experiencing this fate is extremely small, but the galaxy is very old and very large, and improbable events accumulate. It is possible, perhaps likely, that some of the planets orbiting stars today arrived not from the birth disk of that system, but from the void between stars, captured billions of years ago from interstellar wandering. We can now pull back farther. The Milky Way is large. Its disk spans roughly 100,000 light-years from edge to edge. Though this figure becomes harder to pin down the more carefully you look, the galaxy does not have a sharp boundary, but thins gradually into a sparse stellar halo that extends much farther. Within the main disk, estimates of the total stellar count range from 200 billion to 400 billion stars. Additionally, the galaxy may contain nearly as many brown dwarfs, objects too dim to fuse hydrogen in the normal way. Dark matter, which we cannot observe directly, but whose presence we infer from the gravitational behavior of everything around it, is thought to account for the majority of the Milky Way's total mass. Including this contribution, current models place the total mass of our galaxy at around 1.5 trillion times that of the Sun. At the center of the Milky Way, hidden behind thick clouds of dust that block visible light, lies a supermassive black hole designated Sagittarius A. Its mass is approximately 4.33 million solar masses. Around it, stars orbit on paths that would be extraordinary by any other standard, some completing full orbits in just a few decades at velocities of thousands of kilometers per second. A smaller black hole, believed to orbit the central one, adds further complexity to the dynamics at the galaxy's heart. Our solar system sits roughly 26,000 light-years from this center, in a region called the Orion Arm, one of several large spiral arm structures extending outward from the galactic bar. It takes our solar system approximately 230 million years to complete a single orbit of the galactic center. In Earth's lifetime, this journey has been completed roughly 20 times. the Milky Way is not alone. Surrounding it is a collection of satellite galaxies, smaller, irregularly shaped systems that orbit our galaxy under gravitational influence. There are at least 30 of them detectable today, and more are almost certainly present, but too dim or too disrupted to identify clearly. These satellites range from loose collections of a few million stars to more structured systems with billions. The closest confirmed satellite is a dwarf galaxy in the direction of Canis Major, lying about 25,000 light-years from Earth and 42,000 from the galactic center. It is so strongly distorted by tidal forces from the Milky Way that it has lost coherent structure. A stream of stars torn from its core traces a ring around our galaxy, a ghost of what was once a gravitationally bound system. The most prominent satellites are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as faint detached patches of sky. The Large Magellanic Cloud sits roughly 160,000 light-years away. Though its mass is 300 times less than that of the Milky Way, it contains some of the most extreme individual stellar objects in the local universe. Among them is R136A1, the most massive star yet measured, approximately 315 times the mass of the Sun, with a surface temperature exceeding 40,000 Kelvin and a luminosity nearly 9 million times that of our star. If placed where the Sun is, it would vaporize the inner solar system and irradiate everything beyond. As in the Large Magellanic Cloud lives one of the largest individual stars by volume, a red hypergiant whose diameter exceeds 1,500 times that of the Sun. Like Betelgeuse, this object is at the end of its life and will go supernova in the astronomically near future. The Milky Way itself is part of a larger structure called the Local Group, a gravitationally bound collection of over 50 galaxies spanning a volume roughly 10 million light-years across. 3 of these are large: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. The rest are dwarfs, some of them so small and diffuse that they were only identified in the last few decades. Andromeda is our closest large galactic neighbor at roughly 2.5 million light-years. It is a spiral galaxy like our own, slightly larger in diameter, containing perhaps 3 to 5 times as many stars, though of similar total mass. Its most distinctive structural feature is its double core, 2 distinct concentrations of stars visible at its center, possibly the result of a past galactic collision in which Andromeda absorbed another galaxy and retained its core as a separate, dense cluster within its own. Andromeda also possesses significantly more globular clusters than the Milky Way, roughly 400, compared to our approximately 150. This excess is thought to be the accumulated remnant cores of dwarf galaxies absorbed over billions of years. Between the Milky Way and Andromeda, gravitational attraction is slowly winning out over the expansion of space. In approximately 5 billion years, the 2 galaxies will begin to collide. This event is not a catastrophe in the conventional sense. Galaxies are mostly empty space, and stars rarely collide directly, even when 2 galaxies pass through each other. But the gravitational disruption will reshape both structures profoundly. Over the course of several billion years, they will merge into a single elliptical galaxy. The stellar streams, the spiral arms, the distinct identities, all of it will be scrambled into a new configuration. Any inhabited planet within either galaxy would experience, over millions of years, a sky that slowly changed beyond recognition. The third large member of the local group is the Triangulum Galaxy, roughly half the diameter of the Milky Way, lacking a confirmed central supermassive black hole and containing a stellar nursery called NGC 604 that is the largest known region of active star formation in the local universe. Over 150 light-years wide, it hosts several hundred young massive stars whose combined radiation ionizes the surrounding gas and makes the nebula glow brilliantly. We can pull back further still. The local group is part of the Virgo supercluster, a vast flattened structure containing over 30,000 galaxies, spread across a volume roughly 150 million light-years in diameter. The combined mass of this structure is on the order of a quadrillion solar masses, and yet this too is not a closed, self-contained system. The Virgo supercluster is itself a component of a still larger structure called Laniakea, a filamentary superstructure roughly 520 million light-years across, containing hundreds of thousands of galaxies and a mass approaching 10 to the power of 17 solar masses, or about 100 million billion times the mass of our Sun. At the center of Laniakea's gravitational geometry lies what astronomers call the Great Attractor, a region of space generating sufficient gravitational pull to draw entire galaxy clusters toward it from hundreds of millions of light-years away. We cannot directly observe the Great Attractor because it lies in the direction of the galactic plane, obscured by the dense dust and stellar mass of the Milky Way's disk. We know it is there because everything in our region of the universe is moving toward it. What it consists of, whether primarily dark matter, an unusually dense supercluster of galaxies, or something we have not yet categorized, remains unclear. At the largest scales of observation, the universe resolves into a web. Galaxies are not distributed randomly. They clump along immense filaments of dark matter, tracing a structure sometimes called the cosmic web, a three-dimensional lattice of galaxy clusters connected by threads, with vast empty regions between them called voids. Individual filaments can stretch for hundreds of millions of light-years, and then there are the Great Walls. The Hercules Corona Borealis Great Wall, identified in 2013, is the largest known structure in the observable universe. It spans approximately 10 billion light-years. It encompasses regions of space that themselves contain thousands of galaxy clusters. Its mere existence creates a problem for standard cosmological theory, which predicts that structures above roughly 1 billion light-years across should not be able to form through normal gravitational processes given the age of the universe. That the Great Wall exists at all suggests that either our models of structure formation are incomplete, or that the early universe had initial conditions we do not fully understand. Now we approach the edge. The observable universe is defined by a limit that is not a wall, but a horizon. In the roughly 13.8 billion years since the Big Bang, light has had a finite amount of time to travel. Any source more distant than a certain threshold has not had time to send light that has reached us yet. For objects at the edge of this horizon, the light arriving at our instruments departed when the universe was only a few 100,000 years old, before stars existed, before galaxies, before any structure more complex than a hot plasma of hydrogen and helium. The radius of the observable universe is approximately 46 billion light-years. This figure is larger than the age of the universe in light-years, because space itself has been expanding. During the time the light was traveling. The observable universe is a sphere centered on us. Not because we are special, but because light travel time defines what any observer can see, and every observer sits at the center of their own observable universe. The total extent of what we can directly examine or communicate with is therefore a volume roughly 93 billion light-years across. Beyond that sphere, space continues. How far it continues, whether it is finite or infinite, whether it eventually curves back on itself, we do not know and may never know. This is where our tools end and our imagination must carry us. At the boundaries of the observable universe, some objects are moving away from us faster than the speed of light, not violating any physics, but carried by the expansion of the space between us. These objects have already passed beyond reach. Even if we transmitted a signal today at the speed of light, that signal would never catch up to them. They are causally disconnected from us, as separated from our world, as if they existed in a different universe. And perhaps in some meaningful sense they do. Some astronomers have noted unusual patterns in the motion of galaxies near the observable boundary, anomalous bulk flows that seem to point towards something beyond the visible horizon. If such structures exist, vast concentrations of mass on scales larger than anything we can see, their gravitational influence could, in principle, leak across the horizon and subtly influence what we observe. The possibility has been studied and debated. It remains neither confirmed nor dismissed. What lies beyond the observable universe is, by definition, not something we can directly investigate. But theory offers possibilities. One class of hypotheses proposes that the universe, while finite in some sense, is vastly larger than the observable portion, large enough that the conditions we inhabit are replicated elsewhere many times over simply by chance, on scales too distant to ever reach. In an infinite or nearly infinite universe, every possible configuration of matter repeats. There are copies of you somewhere beyond the observable horizon, in rooms that look exactly like this one. This is not mysticism. It is a straightforward consequence of probability applied to a large enough space. Other hypotheses invoke a multiverse, a collection of separate space-time regions, each potentially governed by its own physical constants, its own values for the speed of light, the strength of gravity, the mass of the electron. Our universe would be one among an uncountable number, perhaps the only one with constants finely tuned enough to produce stable atoms, stars, planets, and observers. The multiverse is not currently falsifiable, which places it outside the strict boundaries of science, but it is also not inconsistent with what we know, and several theoretical frameworks that do make testable predictions naturally produce it as a consequence. At the most radical fringe of current speculation lie ideas that challenge not just the size or structure of the universe, but its nature. Some physicists have proposed that the physical world as we experience it may be, at its deepest level, informational, that the universe is a kind of computation with physical laws arising from logical constraints rather than from some prior unexplained substrate. In this picture, asking what the universe is made of is less meaningful than asking what rules it operates by. Whether this framework is more than a philosophical curiosity remains to be seen. What we can say with confidence is this: we live in a universe that is old enough and large enough to be genuinely incomprehensible to the creatures who evolved within it. We are limited by our senses, our instruments, the speed of light, and the age of time. And yet here we are, cataloging the stars, measuring the distances between galaxies, detecting the gravitational echoes of black holes merging a billion light years away, tracing the large-scale structure of space itself from a small planet orbiting an ordinary star in the outer arm of a mid-sized spiral galaxy. The probes we launched in the 1970s are still going. The light from stars that died before the Earth existed is still reaching us, carrying information across unthinkable distances. The universe is not merely large, it is generous. It gives us signals to read, patterns to find, and questions that grow more interesting the harder we press on them. We do not know what lies beyond the horizon. We do not know whether the universe is alone or one of infinitely many. We do not know whether it is temporary or eternal, whether time had a beginning that was the first beginning or merely one in a sequence. We do not know what dark matter is, or what dark energy is, or why the fundamental constants of nature have the values they do. But we know what the inside of Pluto looks like. We know how many stars are in Andromeda. We know the mass of the black hole at the center of the Milky Way to within a few percent. We know what water looks like on a cold, dark, starless world drifting alone through interstellar space. For beings who spent most of their history unable to see past the clouds, that is something remarkable. The universe does not care that we are here. It was here long before us, and it will continue long after any structure we could imagine has been erased by entropy and expansion and the slow cooling of everything. But while we are here, we can look, we can measure, we can understand, a little at a time, the dimensions and contents of the place we inhabit. And that, perhaps, is enough.